Everyone thinks a candle burns simply because it's lit. They're wrong. It's a surprisingly intricate dance of physics and chemistry, a small, self-sustaining inferno powered by unseen forces. That gentle flicker on your dinner table, it's a miniature engine, constantly pulling itself apart and reassembling in a spectacular display of energy transformation. We often take this everyday marvel for granted. You light it, it burns. But what's truly happening at the molecular level? How does a solid block of wax transform into light and heat without ever truly touching the flame itself? The magic starts with the wick. Usually braided cotton, it's not just a string, it's a capillary highway. When you introduce a flame, even briefly, the heat begins to melt the solid wax at the wick's base, creating a tiny pool of liquid fuel. This liquid wax then defies gravity, drawn upwards by capillary action, much like water climbing a plant stem or ink spreading through blotting paper. It's a physical phenomenon, not unlike how blood flows through your own capillaries. But it's not until this liquid wax reaches the top of the wick, closer to the heat of the flame, that the real transformation begins. Here, it encounters temperatures hot enough to vaporize it, turning it from a liquid into a gas. This gaseous wax, now a fuel vapor, is the true meal for the flame. It mixes with oxygen from the surrounding air, and in a precise, furious chemical reaction, it oxidizes. This is what we call combustion, and it's where the light and heat are born. The flame itself isn't a solid or liquid, it's a plasma. It's a superheated, ionized gas, so hot that the electrons have been stripped from their atoms. This intense energy release is what generates the radiant light and warmth you feel. Now here's a curious detail. The flame isn't uniformly hot, it has distinct zones. The inner, dark blue cone, just above the wick, is where the wax vapor is still heating up and hasn't fully combusted. It's the unburnt fuel zone. Surrounding that is the bright yellow zone, the heart of the flame. This is where the combustion is most vigorous, and tiny soot particles, incandescent with heat, emit that familiar warm glow. These particles are actually incomplete combustion byproducts. And on the very outer edge, often a faint, almost invisible blue, is the hardest part. Here, there's ample oxygen, and the wax vapor burns most efficiently and completely. It's where the most intense energy release happens, but with less visible light. Think about that for a moment. The light you see isn't necessarily where the most heat is. The yellow glow is a sign of incomplete burning, a beautiful inefficiency. A perfect, clean burn would be almost invisible, like a gas stove flame. The candle's genius lies in its self-regulating nature. The heat from the flame melts just enough wax to keep the capillary action going, which feeds just enough vapor to the flame to sustain itself. It's a feedback loop, beautifully balanced. This delicate equilibrium is also why a draft can make a candle flicker wildly or even extinguish it. A sudden gust of air disrupts the flow of oxygen and displaces the hot wax vapor, breaking that crucial feedback loop. And what about the wick's length? As a candle burns, the wick itself is consumed, but often at a slower rate than the wax. If the wick gets too long, it can't draw up enough wax efficiently, leading to a weaker flame and more soot. That's why trimming your wick is important. It ensures the flame stays at the optimal height to vaporize the wax effectively, maintaining that brilliant, steady glow. It's a small act that profoundly impacts the candle's performance. From a simple stick of wax to a self-sustaining chemical reactor, the candle reminds us that profound physics and chemistry are at play in even the most humble objects. It's a tiny testament to the universe's intricate design. So the next time you light a candle, pause for a moment. Look beyond the drip and the glow. See the invisible forces, the molecular transformations, and the elegant dance of energy that brings that warm light to life. It's a beautiful secret, burning brightly in plain sight. Uncover more hidden wonders in our next dive into everyday physics.